Hello to everyone, I'm Anna Virginia Lambiase and I will show you the preliminary results of the effect of carbon nanotube in ultra-high performance fiber reinforced concrete. The work was conducted in collaboration with Professor Luciano Feo, Professor Enzo Martinelli, Professor Rosa Penna and Marco Pepe. Well, after a brief introduction and the presentation of the material used, will be shown the kinematic assumption and constitutive law of the Cracked-Hinge model. Next, the calibration of the matrix stress-strain parameters and of the bond slip law of the steel fibers will be presented in order to compare the model prediction with the experimental results. First of all, the experimental results were those presented in this work by Meng and K. Hunt, and were here used to improve the Cracked-Hinge model already developed in this work, in which a mesomechanical approach was adopted. The aim is to predict the response of ultra-high performance fiber reinforced concrete beam element by varying the percentage of carbon nanofiller. As regards the material, six mixture composed of steel microfibers with a fixed content of 0.5% and carbon nanofillers with a variable content ranged from 0 to 0.3% were considered. For the geometric beam representation, a standard spacement transversely notched at the mid-span section was considered. In particular, the model is able to consider the bridging effect offered by the fibers, so the total number of it in the mid-span section was determined as the ratio between the volume of the total fibers and the volume of the single fiber. In particular, a random distribution of the fibers inside the spacement prismatic volume was generated by utilizing the standard random number generator in MATLAB. As regards the model, the principle of the kinematic is inspired to the so-called Cracked-Hinge approach, and it was based on the following assumption. First of all, the flexibility was distributed only in the center part of the spacement, while a rigid body behavior is exhibited by the remaining end part. Then, if we discretize the mid-span section in NC layers, we can evaluate as follows the average axial strain of the KTH layer before crack formation and the crack opening displacement after crack formation. It means that the average value of the axial stress of the concrete at the KTH strip can be determined as a function of the axial deformation before cracking, or a function of the crack opening displacement after cracking. In the end, and as regards the fibers, the bridging effect offered by the fibers was taken into account by introducing the action Fk mobilized at the JTH step of the incremental analysis as the product between the fiber's area and the axial stress that depends on the sliding of the two parts embedded in the two sides of the crack, and it was correlated to the bond stresses but also to the crack opening displacement. For the constitutive law, we refer to the Fib model code for concrete structure. In particular, the concrete behavior in compression is described by this equation, that is related to the strain at the maximum compressive stress and the plasticity number. To describe the tensile behavior, A stress-strain diagram should be used for the uncracked concrete, and a stress crack opening diagram, as shown in this second figure, should be used for the cracked section. In the end, as regards the constitutive law for the short steel fibers, the mathematical relation of the local constitutive law adopted in this study is provided in this equation, where S was considered equal to the crack opening displacement at the level of KTH fiber, while the 5 unknown parameters have to be calibrated using the experimental data. In particular, the nonlinear bond-slip law is divided in 3 different branches: a linear elastic behavior at the stress level corresponding to the matrix tensile strength, a softening behavior characterized by the formation of many microcracks in the mixtures, and a constant behavior. For the calibration, an inverse identification procedure was carried out with the aim to determine the value of the model parameters that lead to minimize the difference between the measured and predicted force displacement curves. In particular, the increase in the fracture energy with the increase in the percentage of nanofiller was taken into account by modifying only the crack opening W1 through the alpha parameters, but also the fracture energy through the initial fracture energy and the initial compressive strength. For the calibration of the bond-slip law parameters, first of all 5 parameters were calibrated for the displacement without nanofiller, and then the 2 bond stresses were calibrated again of reinforced displacement, while all the other parameters were considered constant. Here it's possible to see better the initial branches. In this slide are presented the results, so the comparison between the numerical load deflection curves, which are the colored one, and the experimental curves, which are the black one. We can see that the curves match almost perfectly in the first part, while some differences are presented in the post-crack behavior, where a softening behavior is exhibited for low content of nanofillers, and an hardening behavior is observed when the content is higher than 0.1%. Then it can be noted that the correlation of the stress-strain behavior in terms of fracture energy results in an almost linear correlation with the increase of content nanofiller. At the same time, the back analysis of the bond interaction between the cementitious matrix and the steel fiber show that the increase of nanofiller dosage is linearly correlated to the increment of bond stresses. In the end, the good agreement between the experimental data and the numerical results have been observed. However, future experimental results are needed to calibrate general relationship between the main parameters that control the bond-slip law of the fibers and the stress-strain relation in presence of nanofiller. This will be part of future developments of the present research. Thank you for your attention.